pH scale represents how acidic or basic something is. In aqueous solutions, or solutions where water acts as the solvent, it ranges from 0 to 14, with water measuring at the neutral midpoint of 7. Anything above 7 is basic, and anything below 7 is considered acidic. Bases and acids are two sides of the same coin. Acids have higher concentrations of H+ ions than OH- ions, while bases have more OH- ions than H+ ions. They are inversely related. The higher the H+ concentration, the lower the OH- concentration will be. The product of the two concentrations in aqueous solutions must be 10 to the negative 14th. If you're curious as to why, get excited about this because you're going to cover it in Chem 115. Each step in the pH ladder represents a movement by a power of 10. Since we are dealing with decimals, these are negative exponents. Therefore, the more acidic, the lower the pH number. 6 is 10 times more acidic than 7. If we started with a solution of pure water and then added a solvent and found the pH to be 10, the solution would now be 1 over 10 times 10 times 10, or 0.001 of the concentration that it used to be. The concentration of H+ ions, denoted in brackets, is a function of 10 to the power of the negative pH. Let's look at a graph of H+ as a function of the pH. For a pH of 1, the H+ concentration equals 10 to the negative 1, or 1 over 10. For a pH of 2, the H+ concentration equals 10 to the negative 2, or 1 over 100. For a pH of 3, the H+ concentration equals 10 to the negative 3, or 1 over 1,000. You can see that even though each step cuts the concentration into a tenth of what it was, the earlier steps represent correspondingly larger drops of H+ ions. Now let's manipulate this function so we can use the H+ concentration to get pH. Here are a few equations to help you see how a logarithm rearranges the variables in an equation to make the exponent accessible. Taking the logarithm of our equation gives log base 10 of the H+ concentration equals negative pH. Keep in mind your calculator assumes 10 as the base unless otherwise specified. Let's work a few examples. You dissolve 25 grams of hydrochloric acid in 1 liter of pure water. How does this change the pH? Concentration is a measure of some quantifying part per unit of volume, usually measured in moles per liter. We start with a mass, and we use the molar mass of HCl to go from mass to moles. For every 1 molecule of HCl, there is 1 atom of hydrogen. We also know, according to this table, that hydrochloric acid is a strong acid, so it will dissociate fully into its constituents. Both of these facts tell us that for every 1 mole of hydrochloric acid we add to the solution, we have 1 mole of H+. So now we have an H+ concentration. We can plug that into our equation, and we get that the pH is 0.164. You add 10 milliliters of a 0.3 molar stock solution of nitric acid to 600 milliliters of pure water. What is the change in pH? We are going to use the equation initial concentration times initial volume equals final concentration times final volume. Once again, this is dealing with a strong acid, which has 1 mole of hydrogen for every mole of nitric acid. So we know that the molarity of the nitric acid is also in that 1-to-1 ratio. That is to say that the molarity of the stock solution is the same as that of the H+ ions. And then we know that the final volume is the sum of the water and the nitric acid making up the solution. So we find the concentration, and we plug that in to our formula. We get that the pH is now 2.3, and to find the change in pH, we do 7 minus 2.3 equals a 4.7 drop in pH.